World Spaceflight News Special Report.
Okay. So when we do interface the flight harnesses, the thruster connector saver is also in there. Okay. And then we'll just put those on and those for you guys to repeat the process. Cool. See the holes. I have good on these two corners.
These look good.
Okay.
Well, I guess we'll thread some and see.
I have hands on. Okay.
It's I'm sorry, 3102 and 31.
looks like. Good? Okay, then I'm not 2 points. It's okay, you don't have to do it then. Sorry. Step over. Step. Clear. Alan and I are back out of the way. Okay.
Very good.
But stop.
Bumping south.
Emery, hold off on the crane. We're going to manipulate a little bit and see where we're at. That lines up holes down on the bottom. How are you guys looking in there?
I'm there.
Correct.
To the lock. Bouncing around.
Solo Pro? Yeah, Solo Pro Hockey Sticks.
Everybody good?
Yep. We're ready. Let's go.
I'm in north. Stop.
Stop.
We're free.
Okay, we're free. Let's keep going.
North. Stop.
Stop.
We're free.
Okay, we're free. Let's keep going.
North.
My name is Elizabeth Abel. I am DART's thermal lead. Blankets keep the spacecraft warm, or actually cool in some cases. Making blankets is a lot like making clothes. What you want to do is you want to first take a piece of what we use as Melanex to form your pattern of whatever the blanket you're going to be making. So over here, Minhee is making a pattern of the star tracker. So once you have your pattern, your nice form, then you can take that back to the shop. That's when you cut out your blanket material like you would with clothes. Fabricate it and mold it, and then once you have that done, then you're ready to go and install it on the spacecraft. My team is small, but mighty. It's me as the lead, and then I have an analyst who's helping me out, John Kim, and then I have some blanket technicians, Minhee, who you see working here in the back, and then Emery Toomey. We're a small team, but we're a good team. DART is a great mission to work on. I mean, it's so fun when people ask me what I do. Now I can say, I'm actually working on something that's going to protect our planet. It's a cool mission to work on.
My name is Jeremy John. I am the lead propulsion engineer for the DART spacecraft. I've been responsible for the design and development of both propulsion systems that the spacecraft has on it. The Next-C ion thruster has been installed on DART for technology demonstration during the DART mission. The intent is to show that the spacecraft is capable of operating the thruster at nominal power throughout various operating conditions during the mission. The Next-C team is comprised of a joint venture between NASA's Glenn Research Center and Aerojet Rocketdyne. We are conducting the first flight of the Next-C ion thruster. It is a little bittersweet to know that we are only going to be able to operate for a short amount of time before we impact the asteroid. With help from APL, NASA GRC, and Aerojet Rocketdyne, we have adapted its use during the DART mission.
My name is Ken Watson. I'm the DART EMI lead engineer. EMI stands for electromagnetic interference. So we do EMI testing on spacecraft to make sure that the spacecraft works with each other. Each of the subsystems were tested alone, but not tested as a full system. So our testing is usually done by either injecting noise on the spacecraft or trying to pick up noise that spacecraft's generating. For the most part, we use the same instrument, which is an antenna, and then power amplifiers. These generate the noise that you're going to hit the spacecraft with, make sure that it can still operate, but these antennas can turn around and start picking up any noise that it's generating just from operating. All missions have their own challenges, and due to the nature of this one, it has some very unique challenges into itself. DART's been a really exciting mission. This is really where science fiction meets reality.
Can you hold this? Thank you.
They get pissed. Otherwise, they're going to cinch down. I got you.
I didn't want to just remove them and tell anybody. Alright, kids are coming up.
We are working together Actually, well, okay, going up. That should be good, Andy. Okay, you got a line?
Yes. More harness on the left. I'm sure. Good.
Okay. I've got eyes on it also. Everyone good? So is it all the way up? Yep, it's up. You're the man. I'll tell you what. All right, we're good. Woo! How high do you want me to go, Rick, before you start straining leaving?
Another foot.
That should be good, Andy. Okay, you got a line? Good. Woo! All right, we did it. Well done.
It did look like centroids dropped out before impact to me. But we could choose to do it. How are we still getting telemetry re-impacting? Start some retrievals then.
got step 1.1 filled out in the procedure. I put the run number in the chat earlier. Okay, we're ready to start moving down through the other steps. So guys, just FYI. Yes.
Out of the way and we'll put them from this side. I'll yell under.
I'm good.
Stop. Switching the inside.
Hands on.
Perfect.
Coming up.
The DART high-gain antenna is a new spin on an old technology. These types of slot-based antennas have been around since the 1960s, but whereas in the old antennas can communicate, say, in one direction just for uplink or downlink to a spacecraft, we specially optimized and designed the slot pattern on the DART antenna so that it could communicate efficiently both at uplink and downlink, so that the Earth can talk to the spacecraft as well as the spacecraft can talk to the Earth very efficiently. As DART is on its final approach out to the Didymos system, the spacecraft will be taking lots of high-resolution imagery and sending that back to the Earth. So as that data comes through the spacecraft and then goes out the high-gain antenna, the high-gain antenna will have to track and follow the Earth so that its beam stays pointed back to the Earth. The RF team here for developing the antennas is a very multidisciplinary team. So it involves not only RF designers who know how to manipulate the RF waves, but mechanical engineers who know how to put together our vision of an antenna into something that can be fabricated.
Hi, I'm Mike Buckley from the Johns Hopkins Applied Physics Lab in Laurel, Maryland, and we're here again to bring you inside the DART mission. I'm with Joshua Ramirez of the DART team, and we're in APL's brand new Building 201. Josh, I just want to start right off by saying first, thanks for joining us.
You're welcome.
And two, tell us what you do on the DART team.
Well, my official title is the Telecommunications Integration and Testing Lead Engineer, and what that means, the big words, is I'm in charge of making sure that we can communicate with the spacecraft, which includes the antennas, the radio, and the power amplifiers. Without that, that's how we get all the data back and forth, so it's a very important system.
Hey, so then that's a great way to introduce the question. Is just tell us then, how do we communicate with the spacecraft?
Well, how we communicate from Earth with the spacecraft is we have huge antennas, which are used by NASA and the European Space Agency for this case, and we send out the signal, and the spacecraft has its own antennas and power amplifiers. All that together, it seems simple when I say it this way, but there's so many elements that have to go right. We have to find the spacecraft, we have to align it correctly, and have the right power level and everything, data rate, and it's a very complex system where just to talk to a spacecraft means that basically all the systems on the spacecraft are working correctly.
It's essentially that radio. You're going back and forth, right?
Yeah.
The two-way communication.
The radio is like the cell phone of the spacecraft, but there's all these other systems like the solar arrays, which are giving it power, the avionics, which is like the computer in it, and the Draco, which is the instrument on it. All these things are gathering data, are doing what they're supposed to, and then they go through our radio to us. So if all of those things are not working, then we're not working either.
Well, you're talking about how different things have to work together on this. You mentioned you're the test and integration role on the mission. What does it mean to integrate the spacecraft?
Well, to integrate the spacecraft, it's literally what you would picture when you hear the question, the word integration, which is when we take all the parts and we put them into the spacecraft, which when it comes here, it's just like an empty canvas, and then we put all our boxes, radios, all kinds of different instruments and equipment that go on the spacecraft, and that as a whole becomes a spacecraft. But all of that has been carefully engineered to work with each other, and there's many people behind this that gave it a lot of thought just to make sure that everything was working correctly with each other. And part of why we do the test part is to make sure that it is working how we expected it and meeting the expectations that NASA has for the mission.
Let's talk about those expectations. Just what is DART going to do?
Well, DART is, I'm going to use a pun here, but we're literally throwing a dart at an asteroid that it will be at about 6.8 million miles away, and we're trying to hit a tiny asteroid that's orbiting that other bigger asteroid. And the reason we want to do that is so that we can prove that there's a way of us actually changing the trajectory of an asteroid in case in the future there's an asteroid that's actually going to cause problems in Earth, and we might be able to send a spacecraft, hit it, and change its trajectory to save the Earth.
Right. So talk about the importance, and the same thing too. These aren't asteroids that are headed toward Earth right now.
No.
Which make them the perfect test subject for something just like this.
That's a question that I've gotten from many people is, well, what if you hit it and then you steer it towards the Earth? It's like what we're actually changing is not the bigger asteroid. It's a binary system. It's Didymos is the big one, and then it's being orbited by Dimorphos, which is the smaller asteroid. That smaller one's the one we're hitting, and we're going to change its orbit. The reason we want to hit the smaller one is because it is smaller. It's easier to change the trajectory of that guy than the bigger one. So that's why this is just a demonstration, like a smaller test to know that if we wanted to do something bigger, we could possibly do it.
Right, and I think to be able to see that in that system too, it's easier to observe. You
Yes.
You can watch that smaller moon go around the larger asteroid
because
and watch it.
trying to hit an asteroid that's by itself and trying to move that, you're talking about an orbit that would be maybe years long, hundreds of years it could be, versus this guy is like 12-hour orbit around Didymos.
Okay, so with that, we're talking about the challenge of making that mission happen. How about the engineering challenges? What were some of the bigger ones to overcome just to get DART together?
I mean, the biggest challenge, and you'll probably hear this from anybody, is the pandemic. And it sounds like a logistical issue, but it really was an engineering challenge because it meant that where there used to be 10, 20 people that were in the clean room building, integrating the spacecraft, now you had to minimize the amount of people. So that meant that a lot of people would need to be remote. In order to be remote, you have to either automate things better, plan things better, or plan your integration in a way that it requires the least amount of hands-on, and that in itself was a challenge. We automated a lot of our things, and that was not easy, especially when we couldn't be there in person, because it's not the same where you're not the one actually seeing what the data is real time. So you have to communicate using Zoom, using Epic, which is an electronic version for procedures. All that really helped us a lot, and it wasn't easy.
Well, I tell you, there's a lot going on with DART, a lot of interesting things. But is there something else you want people to know about the mission that I didn't ask you?
Well, there's one thing I wanted to mention, and it's like the importance of this mission. This is the first time that NASA is actually doing a mission for the planetary defense. So it's the first time that we're actually testing that we can save the Earth in case an asteroid is headed towards us. So that is a pretty big deal. You hear about the pandemic and other things happening. If an asteroid is coming, it's going to be really hard to save us from that. And this is taking us one little step closer to that.
Right, so no pressure, right?
Yeah, no pressure at all, yeah.
All right, well, Joshua, thanks for joining us. So again, thank you for joining us for this look inside the DART mission. I'm Mike Buckley for Joshua Ramirez. Thanks again.
Hi, I'm Jessica Tozer here at the Johns Hopkins Applied Physics Lab in Laurel, Maryland, and we're here in the Mission Operations Center. Now, you might have seen places like this in television or in other media that has big fancy lights and large consoles and big televisions, but what we call the mock, really is actually pretty much like this. I'm sitting here with Ray Harvey, who's going to tell us all about what we're doing, why we're here, and what all this stuff is behind us. So first of all, Ray, thank you so much for being here.
Sure, my pleasure.
I would like to also mention that we are abiding by COVID regulations here at the lab and are maintaining all of the requirements for COVID here at APL. So Ray, tell me a little bit about this place. What is a mock?
Okay, good question. It's a Mission Operations Center. So so the MOC is an acronym for Mission Operations Center. So everybody's fields has tons of acronyms, and so we're no different. I'm a Mission Operations Manager, so that makes me a mom, and so I'm very proud of that. So this is the Mission Operations Center. If you look at in the front, there are 3 U-shaped areas. We call those command pits, and so that's where the Mission Operations team sits when they're sending the commands. In the back is where we'd have the subsystem engineers. They're looking at telemetry to verify that their particular subsystem is performing the way they expect it to.
So this is the main sort of central point for how we control and monitor spacecraft.
Correct.
Very cool. So tell me a little bit about your job here in the mock as a mom. What do you do here as the mom of the mock?
So as the mom, I'm pretty much in charge of the room itself. I authorize who can come in and who can't come in to the mock. And then I'm also in charge of the team that operates the spacecraft on a daily basis. I try to make sure things are working.
We need that, you know? So what kind of things are tracked and managed in the mock? Is it everything? Does everything sort of start and end here?
It's pretty much everything. We keep track of what it's doing on a daily basis. You know, we tell it what to do, and then in a day or so we'll get telemetry that tells us whether it did it correctly or not. And we'll keep track of how much fuel's on board and things like that.
So how much is it really like on TV? Is it like that on TV here when things get crazy?
When things get crazy, yes, but we like it when things aren't crazy. We prefer boring. So boring to us is good. That means the spacecraft's doing exactly what it should be doing, and we don't have any problems going on. So if they're outside of launch and commissioning, when we're testing things out, if there are a lot of people in here, that's bad.
Okay, so this is a good day.
This is a real good day.
Good day.
Yeah,
Okay. Are you able to do like cool maneuvers? Can you, like change the direction of the spacecraft?
Yeah. One of the things, or several things that we'll do, are called trajectory correction maneuvers. So the rocket, the SpaceX Falcon 9 rocket's going to head us in the right direction for that asteroid. And as we start getting closer to it, we're going to do little corrections to make sure it's going to get right where we need it to be.
And you can do that right back here.
We send the commands right from here.
What do you think is the most interesting part about the work that's done here?
I don't know about interesting, but important is the pre-launch testing that we do. We do a lot of testing, and we find a lot of problems. And some people get mad that there's problems, but I think it's great when we find problems, because we're going to fix those problems and it makes our system better.
So let me ask you this. What is your favorite part about working here?
Don't tell anybody, but it's probably the people. Because we hire a lot of smart people. They don't have egos. They like working together, and they got good senses of humor, and we laugh a lot. We have a lot of fun doing what we're doing. So I think it's probably the people.
You do realize you're recording, so they might know. Okay. They might find out.
I forgot about that.
All right, so let's talk a little bit about DART. When will we be able to tell when milestones happen for DART? How will we know when it's reached the right location and when the solar, the rollout solar arrays come out? Like, how do we know when these things happen for DART?
So those particular things we're doing right after we get out of the launch vehicle. And so we'll be seeing telemetry that tells us whether or not those things are happening. A lot of other things we don't know about for a couple days, because it happens outside of a contact.
Are there things that sort of let you know, hey, stuff's tracking, we're going on the right direction, nothing to worry about?
I don't know about when you'll find out about the milestones, but we'll know about them pretty quickly.
Well, you're the ones who are supposed to know.
Yeah.
So I'm okay with that.
Okay.
But send me a text message. No, I'm kidding. Okay, so in your opinion, why do you feel like the DART mission in particular is so important?
Well, DART is the first of its kind, the first one that's going to demonstrate a kinetic impact. I think it's pretty important because, you've seen the movies Armageddon and was it Deep Impact and those kind of things. And I mean, we probably don't have a lot of money to do that.
Send Bruce Willis into space.
Yeah. So this is going to show us if we have the capability to move an asteroid out of the way of what possibly wiped out the dinosaurs, to get it out of our way.
This might be the first time that humans have ever actually pushed something in space, to my knowledge.
It's probably the first time we ever tried to. Yeah, I think you're right.
So what are you looking forward to for the DART mission?
I'm looking forward to just start doing it. We've been doing so many tests and everything. It's like, come on, let's just start doing it for real, because I think it'll be a lot of fun.
Done a lot of practice, ready for the game.
Exactly. Yep.
Is there anything else that you would like to add?
No, just go DART. Hope everything works and we smash into that thing.
Well, you heard it here first. This is Jessica Tozer from the Johns Hopkins Applied Physics Lab Missions Operations Center, and Ray Harvey. Go DART.
Go DART.
Welcome to another installment of Inside the DART mission. I'm Mike Buckley from APL Communications, and we are at the Planetary Impact Lab at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. And I'm with APL planetary scientist Angela Stickle. Angela,
Hello.
I guess, welcome. And first, let's even just start right away with, what's your role on the DART mission?
I am the Impact Modeling Working Group lead for DART, so I lead up all of the simulations of the actual impact to try to understand what will happen after we hit Dimorphos.
Okay, so we're talking about impacts.
Talking about impacts.
Is there a better place to talk about impacts than in the Planetary Impact Lab?
Probably not.
Tell us what happens here.
So in this lab, we have a couple of different things. We study impact processes around the entire solar system. So we have a vertical gun range where we can test impacts into different types of targets. So we can use sands or ices or different types of rocks to mimic planets and asteroids, and try to understand what happens when an asteroid or something like DART hits them to understand the cratering process. This is our ejecta catapult, so it's the second main part of our lab, and it is designed to mimic all of the debris that gets thrown up in an impact crater as it travels away from the crater and hits the surface. So we have a catapult here, and you can load material, so sand, or we like to use aquarium gravel actually. The bright colors make it easy to track. Onto this, you pull it back and then you throw it. So we're literally throwing dirt across the room to see how it moves through the air and to see how it interacts on the surface.
So why is that so important? I mean, why do we need to know that information?
So impacts happen all over the solar system, and they happen all the time. They're sort of the most prevalent process that we see on planetary bodies. And they happen really, really fast. It's not something that you can just walk around and see. And so it's hard to understand the physics of what goes on. And so you need to have laboratories like this with specialized cameras and specialized equipment so you can actually understand the physics of what happens, to understand the geology that we see, but also to predict things.
Now, we see things in movies all the time. I mean, they say that happens too fast, right? In movies, it's all slow, right? We're watching these big things come flying in, and it hits this big impact. But you're talking about impacts of all different sizes, maybe not just larger ones, but even smaller ones, tiny ones that you just need to make sure what happens on the surface when something hits.
Yeah, so small things like pieces of dust or small like pieces of paint from spacecraft or something like that can cause damage. They can cause impact craters if they hit like the space station or they hit a satellite and create craters just like we see on planets with the big stuff. So it's important to understand this sort of at all sizes.
Why is modeling and simulation then so important for the DART mission?
So for a couple of reasons. So DART is the first planetary defense mission that's ever been flown. And it's really a test, right? It's right in the name, Double Asteroid Redirection Test. We don't actually know for sure exactly what's going to happen because we've never done it before. And so modeling gives us sort of that best picture of what to expect. It lets us design the mission in a way so that we can be successful. So we did a lot of simulation early on to understand kind of what size of spacecraft might you need, or what velocities might you need to hit at. We also don't know a lot about Dimorphos, right? Every time we go to a new asteroid, it's different than all of the other asteroids that we've been to. And so depending on what Dimorphos looks like, the results of DART could be different. And so modeling lets us see kind of all of those different options so we have a better sense of what to expect, and also then to back out what happened afterwards. It tells us, if we see X, and the model tells us in order to get X, you had to have A, B, and C happen. It lets us know what happened when we can't be there in person to watch it.
So it sounds like we're trying to learn a few things from the DART mission. I mean, it's not just what happens with the spacecraft when it hits an asteroid, but even the properties of an asteroid too. It sounds like there's a couple of things we're trying to learn from this mission.
Absolutely. So DART, obviously, its primary purpose is to teach us about planetary defense and the effectiveness of this technique called the kinetic impactor. And so DART is going to teach us a lot about that. We think we know what's going to happen, but my favorite part of experiments is, when you think you know what's going to happen and then it doesn't happen exactly that way, you learn something. But yeah, it's also going to teach us about the asteroid. So depending on what Dimorphos is made of, depending on if we see lots of boulders or if it's very fine-grained like sand, or maybe it's just one big boulder in space, all of those things will cause something different. They'll cause a different crater to form. They'll cause a different ejecta curtain that we can see with LICHA cubed, and so it can teach us a lot about what it's made of after the fact.
I mean, the large focus of DART obviously is the impact.
Yes.
I mean, we're going to crash a spacecraft into an asteroid, but you've mentioned a couple of other things here too. So, I mean, what do you think is the most interesting thing about the DART mission?
I mean, the impact is, I think, so I'm an impact nerd, so the impact is definitely one of my, I think it's going to be really interesting. But my favorite, like I said, my favorite part about any experiment is being wrong. So I think the most interesting thing is going to be when all of my models turn out to be wrong. Like, I'm actually really excited about that because I think that is when you learn the most.
Yeah.
Right? You think, I know what's going to happen, I know all of these things, and then something totally new happens. To be fair, I think we're going to create a crater, we're going to change the period of demorphose. I think all of that is going to happen. But I think maybe the amount or what we learn about the material properties that we had thought of ahead of time is not going to be true.
Yeah, I mean, right, who would want to think too, like, prove me wrong, right? But that's the essence of science too.
Yeah.
I mean, be able to actually try this, which made me think about what's the most important aspect, what's so important about missions like DART and planetary defense to do these?
So really, I think for me, it's the scale, right? We have this lab, it's awesome. We can do impact experiments, I can simulate them with my models, but those are all really small scale things, right? When we fire projectiles in our gun range, they're like 1/4 of an inch. They're tiny, right? Asteroids are big. They're hundreds of meters, they're kilometers. And so being able to actually get that data point that says, yes, you can go from your experiments in your lab up to reality is really, really important. You can only get that by doing these sort of planetary scale space missions.
Right, some way to get it off the screen, off paper, out of the lab, and into the real environment to actually see it happen.
Yeah.
Okay, so for an impact nerd, right, and from the science aspect of this, what's the most interesting thing about DART, about the fact that you're going to have this up-close involvement with an asteroid?
So I think it's going to be what it teaches us about the cratering process on asteroids, because asteroids are kind of weird. What we learned when we took samples at Bennu and Ryugu is like the surfaces, they're not what we thought they were. You've got these boulders, you have these spots that are just kind of sandy, they're really, really weak. So if you were to walk on them, you might sink, instead of just, it's really strange. And so I think just understanding how that changes the impact process is really important, because that then teaches us later on, if heaven forbid an asteroid were actually coming towards the Earth, it tells us how to better protect ourselves. Plus, it's just cool science.
Yeah, I'm even looking at the pictures behind us here, and these are all different asteroids that we have visited with spacecraft, and look how different each one of them is.
They're all very different.
So even to get this one instance of how one works is incredibly valuable.
Oh yeah. And as you say, they're all different, and every time we go to a different asteroid, we learn something new. And then this will be another data point. This is going to be one of the smallest ones we've ever visited up close. We're going to have these amazing pictures as DART comes in of the surface, and so that'll be just brand new things that we've never seen before.
We've covered a lot here too, but is there anything I didn't ask, or is it just something you want to add?
Yeah, I mean, I guess to reiterate, it's so important to do these tests at scale. Right? We've only done this a couple of times. We've only had a couple of other space missions that purposefully impacted things. We had Deep Impact, we've had LCROSS, and we learned so much from them. And just having these tests at the real scale that teach us the real physics is so important for science, but also for future planetary defense. So DART is so exciting because it's going to give us that data point that we can point to if we need it in the future to extrapolate to other potentially hazardous objects or other asteroids when we're working to protect humanity from space.
And we're all going to be watching that too, as those keep coming in too. Yes. So thank you, Angela, and thank you for joining us. Again, I'm Mike Buckley and Angela Stickle. Go DART.
We're here to do the final flight inspection of the rollout solar array, or ROSA, that will go on the DART spacecraft after these are shipped to APL in Laurel, Maryland. We're at Deployable Space Systems in Goleta, California, right outside of Santa Barbara. The next couple days will entail the final cleaning, the final inspection of these arrays. When they're rolled out and fully deployed, they're almost 10 meters long. This is the last time that
anyone will ever see these arrays fully deployed. Once we stow them here at DSS, they will not be deployed again until we're in space on the DART spacecraft. Part of our detailed inspection entails Andrew looking at the cell by cell on these arrays, again, that are almost 10 meters long. He'll look at them at different wavelengths of light, different angles, just to assure ourselves that we've found every anomaly possible in these cells and they're fully characterized with the entire array, and we know exactly what we have and the condition it's in when we launch. DSS has flown a rollout solar array as a demonstration on the space station. However, this is the first flight mission that rollout solar arrays will be used on for NASA.